going to be talking about mantle plumes as a source of hot material rather than the elementary school model of passing your hand over a candle flame, which leaves behind the hot spot track, but doesn't leave lingering hot material. Plume material has come up from deep in the earth, so it's buoyant, and it's also hotter. And because it's buoyant and low viscosity, once it reaches the top of the base of the lithosphere, it's going to tend to flow in one direction or the other. Simply, we have plume material that's buoyant, and here I've drawn it going up the slope of the base of the lithosphere to the ridge, leaving a hotspot track, but one without the government-approved age progression. And I'm going to go through some basic physics. I've already given away the key point. The second point is ascending material melts. This is true with anything in the mantle. And the plume material may convect at its top, but the base of the plume material, we have buoyant material over non-buoyant material, so that's stable stratification. And I'm going to spend my time looking at geological features. Practical areas, I'm going to talk a little bit about the North Sea and Irish Sea. I'm going to go to North America for Michigan, and I'm going to be talking about various coastal regions of volcanism where plume material is spread across origin, and I'll talk a little bit about interplate earthquakes as an application at the end if I have time. We'll start with Hawaii. When I was an anti-plume person, I decided to try to disprove Hawaii. That I'm going to talk some about Iceland, and then I'm going to get to cases where the slope of the lithosphere is fairly important. This is on the Big Island in a relatively recent dike. In Hawaii, we have the mantle plume coming up. The plate is coming over very fast. Plume material tries to go radially, but it's dragged back by the plate, and we get a stagnation front. This is just a raw bathymetry map. If you correct for plate age, the uplift, and use a more auspicious contour, it becomes more evident. And we have uplift here beginning about 400 kilometers upstream of the main hotspot. Still problems here of how much of the uplift is thermal, how much of it is from chemical buoyancy. The problem in the ocean basins is we have no useful information on paleo depth of the ocean. So all I can do here is interchange space and time. I can not go out to something here and see it's been uplifted 3/4 of a kilometer over the last million years or so, or 500,000 years, by looking at the fossils in it. The deep sea drilling program compiles things in a way that precludes their rational use, and somebody would have to do this study to begin with. Geometry here, cross-section, the plate's dragging the plume material. We have a stagnation front drawn here crudely. We have a line of hot spots. Model this a little bit more sophisticatedly as buoyant material flowing underneath with drag. It gives you virtually the same answer. This is probably the physical answer if you're trying to explain it to somebody. This kinematic addition of plume radial velocity from the plume and drag velocity from the plates is a good way To explain it, it's a good way to draw a schematic of a swell. The buoyancy is probably closer to the physical answer. Use simple calculations here. You can calculate the nose to the swell and the excess temperature that comes out in the government-approved manner. The shape of the stagnation front, no matter how you calculate it, comes out the right shape of the swell. Historically, I did the calculation to just prove that a plume could make the swell, and suddenly realized that I had an explanation for the swell. I do admit that I spent 2 weeks trying to find an error in my calculations, but I switched camps pretty quickly. Iceland, we have a plume coming up beneath the ridge. The hotspot track has been this way, so the early ridge jumps are towards Greenland. The later ridge jumps, including the one that's going on now, are towards Britain and Scandinavia. The plume material can melt a lot here. You have a relatively slow-spreading ridge, so the lithosphere gets thick in both directions. There we can calculate the affected area. We know the thickness of the lithosphere, so we can calculate the mass balance, the excess temperature for this amount of melting is similar to Hawaii. It's actually a much weaker plume than Hawaii. If it was out somewhere on the Pacific plate or even on the Pacific rise, we'd have trouble seeing it. But just because it's optimally located here on the slow-spreading ridge, we can see very drastic effects. The key here, quickly with pressure release melting, material comes up, drawn here very schematically, intersects a point here where there's significant melting. The latent heat of melting depresses the temperature, and a point like Iceland will reach a point where we have about 25 kilometers thickness of crust compared to there. 1350 would be a more modern number, but the diagram would just be shifted over. The melting begins at a fairly great depth underneath Hawaii significantly, and we need a maximum excess temperature at about 300 degrees for both places. So, plume hypothesis works very well for these very good examples, and we now calculate the crustal thickness also. If you're worried about end-driven convection, number one, the models that purport to show it are not in that domain that's at all relevant to the Earth, and you'd have to recirculate the material 4 times through the melting zone at Iceland to get that. The chemistry would differ, and this idea of recirculating the metal many times to get a hot spot with the same temperature of metal just doesn't work. Okay, back to slope-driven flow, back to cases that are not self-evident, cases that we don't understand very well now. We have the Shishin seamount, Euterba seamount. The hotspot track is there. The paleo ridge is here. You can see paleo fracture zones, and the material flows from the plume towards the ridge and leaves these series of hotspots. We don't know whether these are just places where material got up to dikes that they don't have deep support, or whether we have these individual viscous figures of flow underneath the lithosphere. We have other examples here. We have discovery hotspots. They're obviously flow. Material flows to the young to the old side. From the old to the young side is flowing to thinner lithosphere, and then flows and creates a weak on-ridge hotspot. So this is another example where the flow just weakly reaches the axis, and we have a slightly Kilder axis here that works fine.